In this module, we will discuss the pressure and temperature dependence of equilibrium composition. We have previously emphasized that a meaningful way to describe the composition of a reaction mixture is by using the mole fractions denoted by X. When a chemical reaction reaches equilibrium, the mole fractions of the gaseous reactants and products are related by the equilibrium constant Kx. Kx is defined as the product of the mole fractions of the gaseous reaction participants K, each represented by xk, raised to the power of their respective stoichiometric numbers nu k. It is connected to other system variables through this equation. In this equation, P stands for the total pressure of the system, while T denotes its temperature. Delta RG standard represents the standard reaction Gibbs energy at temperature T, while delta nu is the sum of the stoichiometric numbers for all gaseous reaction participants. The chemical composition of a reaction mixture in equilibrium, as captured by the equilibrium constant Kx, is ultimately a function of externally set temperature and total pressure. In this module, we will explore how changes in temperature or pressure impact the equilibrium composition. To explore how temperature influences the equilibrium composition at constant pressure, let us re-examine the formula for Kx. We express the standard reaction Gibbs energy using the standard reaction enthalpy and entropy. From this formula, we can derive the natural logarithm of Kx. When considering a narrow temperature range where both the standard reaction enthalpy and entropy are almost constant, we deduce the following relationship: the partial derivative of the logarithm of the equilibrium constant with respect to temperature at constant pressure equals the standard reaction enthalpy divided by the product of R and the square of the temperature. This equation indicates that the sign of the standard reaction enthalpy determines the direction in which the equilibrium shifts when temperature changes. If the standard reaction enthalpy is positive, indicating an endothermic reaction, an increase in temperature causes the equilibrium constant to increase. This means there are more products in the reaction mixture in equilibrium. It is described as a shift of the equilibrium composition towards the products. Conversely, in an exothermic reaction, where the standard reaction enthalpy is negative, a temperature increase leads to a decrease in the equilibrium constant. This indicates that the composition of the reaction mixture in equilibrium shifts towards the reactants. The observed effects are opposite when the temperature decreases. Now let us examine the pressure dependence of the equilibrium constant at constant temperature. This is the equation we had started from. Here, the pressure dependence is manifested in the term ratio of P to the standard pressure raised in the power of minus delta nu. The term delta nu represents the difference in the stoichiometric coefficients of gaseous reactants and products in a balanced chemical equation. Its sign directly determines how the equilibrium composition responds to pressure changes at constant temperature. positive delta nu indicates that more gaseous products are formed in the reaction than the gaseous reactants being consumed. In this case, an increase in pressure will favor the reactants. If delta nu is negative, more gaseous reactants are consumed in the reaction than the gaseous products being formed. In this case, an increase in pressure will favor the products. Finally, if delta nu is zero, the equilibrium composition is unaffected by pressure changes. The shift in equilibrium composition due to temperature or pressure changes align with the qualitative principle proposed by the French chemist Le Chatelier. A system in a dynamic equilibrium, when subjected to a disturbance, tends to respond in a way that minimizes the effect of that disturbance. It is important to understand that the equilibrium must be dynamic in nature. In this state, the system is not hindered from adapting, allowing it to respond to external changes. Now, what would count as a disturbance? A disturbance can arise from a change in the amount of reactants or products, a change in pressure, or a change in temperature. For example, if reactants are added to an equilibrium mixture, the system will naturally proceed towards producing more products to restore the disturbed equilibrium. When the external temperature increases, the composition of the reaction mixture will shift in the endothermic direction. Simply put, the system will absorb the added heat. On the other hand, when the temperature decreases, the composition of the system will shift in the exothermic direction. This can be considered as a heat release by the system to compensate for the temperature decrease. This behavior can be rigorously described by the equations introduced before, but it can be also deduced from the qualitative insights provided by the principle of Le Chatelier. Pressure changes affect the equilibrium composition in a similar fashion. When the total pressure of a system in equilibrium increases, the system shifts its equilibrium composition in the direction with fewer gas particles. Essentially, the system tends to shrink to counteract the increased pressure. On the other hand, when the total pressure decreases, the system compensates it by moving the equilibrium composition towards the side with more gas particles, causing it to expand. These effects can be rigorously derived through the definition of the equilibrium constant Kx, but they can also be deduced intuitively using the principle of Le Chatelier.